Today we're going to look at some geometric series practice and applications. So you already know what a geometric series is. It has a ratio between terms, and we know our formula for a infinite series. For a finite series, this formula is fine. I said it could be used. I said, or you could just use the summation on your calculator. So that's probably what we're going to stick with here. So the nice thing about geometric series is that it actually gives us a more accurate look at investments. So usually someone doesn't just put in $1,000 and let it sit for 20 years. They're actually investing money every month. So the money is growing and their older investments are growing with interest. So it says, suppose you invest $100 each month in an interest-bearing account. It has 3% annual rate of interest. So you get 0.25% every month, but 3% is the annual. That's what we're going to be using. The amount of money that you would have n months takes this form. So let's just say that your money's been in there. Let's say it's April. You invest $100 in April. Well, you also invested $100 in March, and that has earned interest just since March. So there's your 1.0025. Now you invested $100 in February. That $100 has earned interest over 2 months, March and April. And then this would represent the money you invested in January, $100. It has earned interest over a period of 3 months. So the further you go out, the longer that your initial investment is gaining interest. And your most recent investment, right, is not gaining interest until the next month. So it says, since in these cases the monthly return rate will be greater than 1, we can only find the sum if the series is finite, right? Our ratio is 1.0025, which is bigger than 1. So we can only find the sum if the series is finite, so many months. So this means that we would use this formula or do it on our calculator. So I said, let's use the finite formula to determine the money in the account after 6 years. Let's just skip using the finite formula. Let's write out a summation and use our calculator to verify that. So we were saying, oh, oops, I need this 6 years right here. So we want to use this information, right? $100 each month, 3% annual rate of return, and it's monthly interest, so monthly compounding. And we want to know how much would be in the account after 6 years. So we want the sum, n goes from 1 to, how many times would we want to compound this? So we actually want to compound it 6 years times 12 months. So isn't that number going to be 72? I'm going to do 72 compounds. And what is my formula? $100 every month times 1.0025 to the n minus 1 power. Why is it n minus 1? Because when I plug in 1 for my first month, I don't want to get any interest, so I just get $100 back. And then when n is 2, I would get what was up here, this 100 and then this 100 times 1.0025. So it was 3%. Instead of doing 3%, I did 3% divided by 12. So that's my monthly rate of return. N is representing my months. So let's see what I get when I do that summation. So math, summation, x goes from 1 to 72, 100, parentheses, 1.0025 raised to the n minus 1 power. So it's thinking for those 72 compounds, so I'd have $7,877.94 in the account. That's not too bad. Let's think about how much money of that I put in. $100 times 72 months, times 72 months is $7,200, right? So like $600 of that was interest. $7,200 I put in myself. All right, so let's see, instead of $100, how much should you invest each month at that compounded monthly rate so that I'll have $15,000 at the end of 6 years? Well, a lot of this is going to stay the same. So if we set up a similar summation to what we just did above, 15,000, that's equal to the sum n goes from 1 to 72 still of x. I don't know how much to invest each month. I still have that rate of return, right? The 3% divided by 12 for the monthly to the n minus 1. So I want to show you an interesting property for summations. For summations, you can actually pull this constant out in front of the summation because it's really going to be this number 72 times. So if you actually do the summation on this amount is going to be a number. And you can take this number and divide it to the other side, and that'll say, all right, I'm getting rid of my interest. What does my monthly investment have to be? It'll be X. So I want to show you, if I put in my summation, n goes from 1 to 72 of just 1.0025 raised to the n minus 1. So I'm not putting in a number for my first term. That gives me this number, 78.77. So I would have 15,000, I'm still just continuing my work, and I ran out of room, equals X times 78.779, right? 78.779. That was the summation. I still have this constant here. I'm just going to divide that number to the other side, 15,000. So 15,000 divided by my answer. I need to invest $190.41 every month. So $190.41. So that kind of makes sense because up here with $100, I got to what? Not even 8,000. I want to get to 15,000. So I almost have to double my monthly investment, right, to get to 15,000. Number 4 is a slightly different question. How much should you invest each year at 5% annual interest compounded annually this time in order to have $75,000 at the end of 20 years? So let me get a blank sheet of paper to do this problem on here. All right, so I'm doing the 75,000 as my answer. The sum n goes from 1. How many times is this getting compounded? Only 20, right? Compounded annually for 20 years. 1 to 20. I don't know what I'm investing. And I'm just getting 1.05, right? Because the 5 doesn't have to get divided by 12 because 5 is annual to the n minus 1 power. So I'm going to kind of pull that same trick. I'm going to pull out this constant. I'm going to do this as a summation, and I'm going to divide my answer to the other side. So I'm going to do the summation, math summation. N goes from 1 to 20 of 1.05 raised to the n minus 1 power. So I get 33.06 over here times x equals 75,000. So I need to take that 75,000 and divide by that 33.06. 75,000 divided by my answer. I'd have to invest $2,268.19, or probably round up to 20 cents, or I'm going to be short. Every year. I'm investing each year, right? Annual interest, so investing each year. So that would make sense. So in order to have $75,000, I have to invest $2,000 a year for 20 years. How much is that times 20? I'm putting in $45,000 of my own money, and I'm gaining like $30,000 of interest over 20 years. So that's not bad. So $2,268.20. All right, so that's kind of the big idea. You can solve for your missing principal by doing the summation only on the interest and dividing it to the other side. So here's kind of part 2 of an idea related to geometric series. So this time, This is talking about chemicals going into a holding pond, and it's going to be an infinite series. Remember that the formula for infinite is you take your first term and divide by 1 minus your rate. So suppose a logging company treats logs with a toxic chemical that enters a holding pond. There's 8 kilograms entering the pond at the beginning of each month. During the month, 40% of the chemical in the pond dissipates. Find the amount of chemical in the holding pond after 3 months and the amount of the chemical in the pond if the process continues indefinitely. So I throw some chemicals in the pond from whatever process. 40% of it goes away, but I keep 60%. So if you notice, 60% is the amount I'm retaining. So after 1 month, yep, there's my 8 kilograms. After 2 months, I'm throwing in 8 new kilograms, and I have 60% of what I started with from the month before. And then I've got still 60% of that, 60% of that, and my new 8 kilograms. See how they keep sliding over? So this one keeps dissipating, keeps dissipating. The newer one starts dissipating, keeps dissipating, right? So what is S sub 3? So I could just add together those 3 terms if I wanted to. 8 plus 8 times 0.6 plus 8 times 0.6 squared. I would have 15.68 kilograms. So it says find the infinite amount. So if I keep going forever, eventually it's going to plateau at a certain amount. So I'm going to take my 8 kilograms, 1 minus 0.6, and see what that gives me. It gives me 20. So it's going to plateau at 20 kilograms based on my infinite formula. If I keep going forever, remember I keep adding smaller and smaller amounts at the end. It says, will the maximum concentration in the holding pond ever exceed the federal limit of 22 kilograms? So never, right? All right, what about, will the maximum concentration ever exceed the state limit? So the state has a lower limit. So yes, it will exceed. It will. So we need to figure out after how many months, right? So let's do a summation, math summation. N goes from 1 to, how many months do you think? 8 months? I don't know. 8 times 0.6 raised to the n minus 1. At 19.66 after 8 months, 9 months? Nope. I'm guessing and checking how many months by just changing it. 12 months? Nope. Getting closer. 15 months? Almost. How about 18 months? Oh, still not yet. How about 24 months? That would be 2 years, right? Oh, still not yet. How about 36 months, 3 years? Nope, still hasn't exceeded. Oh, wait, we want it to exceed 19. Oh, go back. What did I start with? Oh, even at 8, it was over the 19. Oh, my bad. Sorry, can't go back and delete this. Real life teacher problem solving. All right, delete, let's say 6 months. Oh, that was already over 19 right there. What was 3 months? 15. Jumps up pretty fast. How about 5 months? It's over 18. Okay. We want it to be over 19, right? So 5 months is too little. 6 months is too much. 6 months. So that was guess and check. All right. So I'd like you to try these 4 examples today. You might have to do a little bit of work and look back about geometric series. You might have to do a little guess and check. Let me know if you have questions. It's going to take a little bit of problem solving, but you are working on 157, and you only need to send me these examples 1 through 4 today through Google Classroom.